Hello, or welcome back to this channel. Today we're going to talk about the network functions, which is a different concept from what we did in the last chapter. So we are starting in chapter 11. And in chapter 10, we basically learned how to solve the circuit in the S domain, right? So all the detailed circuit, we can find the current and voltage, so on and so forth. And today we're going to look at from a different perspective in terms the so-called network function. And instead of going into the details of the system, and we're trying to characterize the system from the input or output, this perspective. Okay, so there are three topics. First, we're gonna start with the concept of network function, and then we're gonna look at two sort of important types of the network functions for one port and for two ports, and for two-port networks. And so let's start with the network function concept. So the network function is the ratio between the output response, the transform, and the input transform. So the network function is defined still in Laplace domain, but in the perspective with the input and output. So let's see if you have a network and you have some sort of input. Maybe let's see, we call the input in S domain or the input transform. We denote this input as with the XS, and you have some output or the response. And in the S domain or the transform of that response waveform, and that's Y, YS, and this is the output. The output or the response. So in this case, we denote the network function as a TS. And so in this case, here we have a TS. And in this case, the network has zero initial conditions. And we are looking at the ratio between, so the zero state, and if the network has zero initial conditions, that means all the inductor currents and the capacitor voltage at t equal to 0, they are all zeros. And the output in this case, here this YS, and this is the XS. And basically the network function is a ratio between YS and XS, right? So it's very important to know that although the network function is defined as the output over the input, but it is determined by the internal elements and how they are connected by the network itself, right? Just to keep that in mind. So based on this concept, let's see whether this is useful, right? So let's see if we have this network function let's see if TS and XS are known, and we can find the output or the response transform YS by using, since here we have TS equal YS over XS. So therefore, YS is going to be equal TS times XS. Right? So if you, let's see if the TS has the simple poles and they don't have any multiple poles or identical poles, and XS also has the simple poles as well. So we can do the partial fraction expansion on YS. So by PFE, or the partial fraction expansion, and we can write this in the form of the residues over S minus Pj. So this is the Pj would be the poles, or the poles of the Ts, and P sub L. So of course here J is equal 1 to all the n, and P sub L, L equal 1 to m, are the poles. So this is general discussion, and just to see how useful the concept of the network function is. And they are the poles of xs. And then if we take the inverse Laplace transform, right? If we take the inverse Laplace transform, yt is going to be equal the sum of the kj, the residue times e to j, e to p sub jt, and plus the j, the L, use L here, L equal 1 to m, and k sub L times e to p sub L t. So, and we can identify this as the natural response. Natural response. And we also know this as the transient response. And this is what we call the forced response, because this response here is due to the input, right? The force we applied to the system. So that's the forced response. And also we call the steady state response. And that's what we you see, if we know the network function, and we can figure out the output. And also you see the network function will carry the information, carry the poles. So this is the network function Ts is determined by the network itself, not the input, not the input or output, right? So although we define this network function in the form of the ratio between the response Ys and the input. So let's look at an example and see if we can get a better kind of the understanding of this thing. Okay, so let's see, I have this simple first order system, right? And so the first thing is, let's see, find the network function. And after we find the network function, we're trying to find the response I sub 2t. Okay, so this is the current through this inductance here, the network function here. And so in this case, and we're trying to find I2 over Vs. Sometimes if you can't really see this immediately. So in this case, we actually can see this quite straightforward, because I2 over Vs, that's just the admittance, right? Admittance, because this I2 is the same I here. So this admittance is seen by this voltage source. You can do using that way, or you can just do the solve the I sub 2s with V sub 1s as the known, right? So let's see, do in the two ways. So first one here is, let's see, we do the admittance. So the Ts here is just equal the admittance, which is the 1 over 1 plus the 0.001s, which is 1,000 divided by s plus 1. So this is the one way we can plus 1,000. This is one way you can figure that out. So, or alternatively, you can just solve I2. You treating, well, we're treating V sub 1 as the input, as the unknown, right? So in this case, we know I sub 2s is going to be just equal v sub 1s over 1 plus 0.001s. So therefore, the Ts is equal I sub 2s over v1s is just equal 1 over 1 plus 0.001s, which is equal 1000 divided by 1000 plus 1000. Okay, so that's for the how we find this network function. Although this is super simple, right? So that's the sort of two ways that we find. If sometimes you can see the current division, voltage division very easily, you can get a ratio without going into the detail of solving the circuit. You can do it that way, or if you can, you just solve the circuit with the independent variable as a known. Okay, because you're gonna take the ratio. So that's the one. And also once we find the network function, if we know the input, right? So in this case, so this is the first question. The second question, we're asking to find I2 is equal Ts times V1, right? V1 is known. So here we have 1000 over S plus 1000, and V1 is 5 over S, right? So in this case, we need a partial fraction expansion, right? So in this case, let's see, this is going to be equal to K1 over S plus K2 over S plus 1000. So in this case, based on the rule of sum of residues, and we know K1 plus K2 should be equal to 0. Keep that in mind. So K1 is equal to S times I2S, and we evaluate that this pole. So in this case, we get 5000 over S plus 1000, and we evaluate that S equal to 0, so this is equal to 5. And K2 should be equal to -5, so S plus 1000 times I2 S equal -1000, and that's equal 5000 divided by S, right? So in this case, S equal -1000, so we got -5. So therefore, I2S is equal to 5 over S plus let's just write the minus here. So minus 5 over S plus 1000. If we take the inverse Laplace transform I2t, it's just the inverse Laplace transform I sub 2s. That's equal to 5 times ut. I'm going to write the ut later. And minus 5 times e2 minus 1000t and times the ut. And the unit should be amps. Okay, so that's the concept of the network function. Hopefully you get a rough idea what the network function is. And next we're gonna look at the important type of the network function for one-port network. Okay, see you in a moment.